Bismillahirrahmanirrahim. So today we are going to do the inverter DC characteristics, and this is the third slide on the RC delay model. So as you know, let's look at the inverter. The inverter schematic is on the right here. So the inverter consists of a PMOS and an NMOS. When the input is high, Vin equals to 1, the NMOS will turn on and the NMOS will produce different current based on the VGS. So if the VGS is low, the current produced is low, and if VGS is high, the current is also high. Okay, and this is when the NMOS is active. Conversely, when Vin equals to 0, the PMOS is on and the PMOS will start to pull up the output to VDD, and there will be current ID as P. So the graph, the current here is negative because they consider the current flowing from VDD to Vout is in this convention. This shows that it is negative of IDSP, so the current is negative. So this graph is for when the PMOS is on. Okay, the same thing, if you increase the VGS between the gate and the source of P, you can also increase the current. Okay, so if we flip the curve, so if we flip the previous curve of the PMOS, here we put it, we flip it up, we flip it on the x-axis, so it will be here, and then you flip it on the y-axis, it will be flipped onto this way, onto the NMOS line. We can look at it here. So this is when you flip the PMOS current. This is the PMOS current to the positive x and y axis, right? This current will intersect for the same, at the same VGS, the current will intersect at a certain point. This is the switching point, right? So for example, if your voltage is from 0 to VDD, right? So at a certain point, the PMOS will turn off, right? At this point, the PMOS will turn off and the NMOS will start to turn on. So for different input voltage, right, Vin, you can have different current. So this is the intersection point of when the NMOS and the PMOS, the PMOS starts to turn off and the NMOS starts to turn on. In order to have a good intersection here, we want to have beta P equals to beta N. In this case, you have mu P, which is much lower than mu N, so therefore you have to increase WP to be much bigger than WN. Okay, so this is known as the load line. Okay, so with the load line, you can transform it into the voltage transfer characteristics. The voltage transfer characteristic is the graph of Vout versus Vin. So how do they create this graph? So for example, Vin here is 0. So what is the output voltage? So if for the transistor, for the inverter, sorry, okay, if Vin is 0, Vout will be VDD, because the PMOS is on, so the current will be pulled up. So this will be active, right? So at each point you can transcribe these points here, V in and V out to the voltage transfer characteristic curve. So we can look here in the region of A, in this region here, this one the PMOS is on, so the PMOS is linear and the NMOS is off, so the NMOS is in cut off. In the region B, right, the NMOS, the PMOS will start to, before it starts to turn off, it will still be linear, and NMOS will start to turn on, right? Once you have reached the, you have increased the voltage to turn on the NMOS, that is when the NMOS will be in saturation. At this point, at the point C, you can see that both transistors are on. So NMOS and PMOS are on, and this is where they are both in saturation region. And here in the D region, right, the NMOS is linear and the PMOS is in saturation, and finally here the PMOS will be completely off in E, and the NMOS, the only one will be, NMOS will be on, and the output voltage will be pulled down to ground. So the output is low, but the input is high. So you did this in your lab. In your lab, we had to change the size of the size of the transistor. So you want to make beta P equals to beta N, where beta P is equals to mu P times COX W over L P, and equals to Wn COX W over L N, right? So if mu N equals to double of mu P, so in order to make beta P equals to beta N, you have to double the width of WP. Okay, so what happens if you make you don't put this equation into place? You will have something that is called a skewed gate. That means the voltage transfer characteristic will move either to the left or to the right. So it is based on the beta P over beta N ratio, right? So if you make beta N is bigger than beta P, so the graph will move to the left, and if you make beta P bigger than beta N, then you will make the graph move to the right. So it is called a skewed gate, and the output will not be equal.